So today we'll start directly with pose of a robot. Where we started yesterday, we started with special descriptions, where we know we are sticking to serial robots. We are sticking to serial robots only, and we won't be discussing any parallel here. So these are the types of robots that will be covered from now on in this course. Okay, so you know now what is kinematic pair. You also saw what is degrees of freedom, how it is defined, and how Grubler criterion can be used to calculate degrees of freedom. You saw one of the example also, and you also did few examples here. Two more if you have done it at home. And robot frames. This is where we started with industrial serial robot. We saw what are frames, where are important locations where these frames can be placed so that we can define robots so as to model it properly, so as to analyze it, so as to solve for its kinematics and dynamics later on, and sometimes using control, how to control those frames will be useful as well. Okay, even if you want to do any gaming on these robots or any simulation or animation of this robot, then also these frames are very useful. Okay, so we start again with pose of a rigid body. It is a serial chain rigid bodies which are industrial robots. So we'll see how matrix vector representations are made to represent industrial serial robot. These are some of the notations we yesterday we discussed already. Okay, these are some of the symbols notations which I'll be using. Okay, so here we go. We start with a point in space. We start with a point in space. How a point in space is represented? In a Cartesian system, we normally prefer to have x, y, z as coordinates along three orthogonally perpendicular axes, and a point P is represented as A, B and C, whereas A is along x axis, B is along y axis, C is along z axis. Okay, and in terms of vector, it can be written as, now you see this P being a vector. What is this vector? This is nothing but a position vector which connects the origin of the coordinate system or the frame to the point location. Okay, the frame which is placed at P, we connect directly to this. Okay, okay, so exactly this is the vector. Okay, and this is your P vector. Okay, so over here I have used my notation, that is P as a bold, small, capital. Okay, so this is what, and then it can be written as in vector form as axi plus byj plus czk. Okay, that is a standard notation, you all know that. As a coordinate, P can be written as ax by cz in closed brackets. Okay, in matrix form, as this is where this is very important. Now in robotics we write it something like this. We write it as ax, by and cz in a vertical column format, and last part is a variable that is written here as weightage. Sometimes it is equal to 1. In case of robotics, we prefer taking it as 1 all the time. Okay, so it becomes a ax, by, cz 1. So this will be our point format. We'll represent all our points like this. Okay, we'll represent all our points which is in space like this. Okay, okay, moving ahead. So now how a frame will be represented. Okay, each unit vector are mutually perpendicular. If it is a vector triad, a frame which is attached to a body, or if it is floating in space, doesn't matter. Okay, this also has three orthogonal components. Unit vectors along each orthogonal components are represented as normal n. Okay, it is known as normal, orientation and approach vectors. Okay, sometimes it is known as normal, orthogonal and sliding vector. Normal, orthogonal and sliding. Okay, normal, orthogonal, NOS is also there in few books, doesn't matter again. So these three vectors forms the frame, and that is attached to different joint location, to the link location, to the end effector, to the robot base, to the universal frame, and to the body which we want to manipulate. Okay, so all these are represented in similar manner, the manner we expressed our position. It is also written as nx I ny j plus nz k. What are nx, ny, nz? Are three components of n, along x, along y and along z direction. Clear? What is n? N is the unit vector, okay. So we'll put a cap here. N has got three components. It has nx, it has ny, it has nz. Three components. So this makes this n complete, and this is a unit vector. That means nx square plus ny square plus nz square root over will give you 1. That means magnitude of this vector is 1. Okay, and this is your normal vector. Then comes another vector which is again similar to n. It is directed orthogonal to n. Both of them are mutually perpendicular. O also will have three components, Ox, Oy and Oz. And in terms of matrix, it can be written as Ox, Oy, Z transpose, because we want everything to be represented in a vertical manner, okay, column format. Similar to this, there is a vector which is known as approach vector, or sometimes a sliding vector, NOA or NOS. So A is perpendicular to both of them. Okay, all three of them are mutually perpendicular to each other, orthogonal to each other. So A is again expressed in a similar manner. So now a frame is a combination of N, O and A vectors. Okay, each of them are unit vectors, and the frame can be written. Now this is a matrix. So I have written it as bold, capital, okay, straight. So it is n vector, O vector and A vector. In column vector, it is a 3 cross 3 matrix, and this represents the frame. Okay, this is how we'll represent frame from now on. Okay, now moving ahead, a frame in a fixed reference frame, a frame with respect to another frame, will now be represented as this. Now this frame is dislocated. It is not located at the origin itself. Okay, this is now dislocated with respect to the base frame or the universal frame, origin O. Okay, so that OF forms a vector, and P is the position vector, which is given by Px, Py and Pz. Okay, transpose. So it becomes a column vector once again, and in vector format you can write it as Px I, Pyj and Pzk. It is the position vector of OF. Okay, and F frame is now a combination of a frame and position of that frame with respect to the origin O. So this 3 cross 3 vector, sorry, this 3 cross 3 matrix is the frame, okay, frame itself, and Px, Py, Pz, these three defines the position of this frame with respect to origin. Okay, and what is this? In order to make it homogeneous, we will tell you what is homogeneous. We write it as 4 cross 4 matrix. Okay, so this consists of NOA, that is nothing but orientation of this frame. So this frame orientation is given by this 3 cross 3 matrix, and this gives you the position of that frame. Okay, so this is a homogeneous transformation matrix of the frame F, which is nothing but it is expressing the orientation of the frame in space and position of that frame with respect to the reference frame. Okay, this needs further understanding of translation. We'll come to that. We'll also tell you what is a reference frame now. Okay, going next, a rigid body is defined by a frame which is attached to that. Okay, because you know a rigid body is defined as a distance between any two point on that solid object doesn't change with respect to with time. Okay, they remain together, binded together. They are not going to change. Neither the orientation of each one of them is going to change with respect to the other, nor the relative position of each one of them. Okay, so this is a solid body. So a frame which is attached to a body remains relatively static with respect to the body all the time. Okay, so now wherever this frame will go, the body will go there. Okay, however, any way this frame is oriented, the object will also be oriented, the solid body will also be oriented in a same manner. Okay, so this frame is now a replica of whole of the solid body. Okay, now this object can also be referred using the same frame as we did it earlier. In the earlier slide you saw NOA defines the orientation of that object and Px, Py, Pz now defines the position of that object, okay, with respect to this reference frame. One is what? This is just to make it a homogeneous transformation matrix of 4 cross 4. Why this is important? We'll come to that. Okay. Now, how a transformation is defined? A transformation matrix is defined as an operator given by 4 cross 4, the way we saw it here. Okay, this is when applied to a position vector represented in a column matrix form makes a movement in space, okay. So if you have a transformation matrix, this is applied to a point which is Px, Py, Pz 1, okay. This creates a new point in space given by Px dash, Py dash, Pz dash 1. So this transformation matrix is an operator. This should be, because it has to be multiplied with this matrix. So this also is a 4 cross 4 transformation matrix. This is now multiplied with this to get a new location and orientation of this point. Got it? So this is what is a transformation matrix. Okay, we'll see how it works, how different transformation can be done. Okay, going to this, it can be a pure translation or it can be a pure rotation. It can only do orientation changes without transforming it to a different location. Okay, so or it can just be a translation without any orientation changes, or it can be a combination of translation and rotation, not just rotations. That means multiple rotations can happen simultaneously. Okay, so that is what is a transformation matrix. A general homogeneous transformation matrix is an operator which will look like this. Got it? Whereas this 3 cross 3 matrix extracted out of this transformation matrix in the form of R3 cross 3, which is a sub matrix, this is responsible for rotation operation, and the term which is here, the column matrix at the last column of this transformation matrix, this performs the translation operation in 3D Cartesian space. How it does it? We'll again have a look at that. And this is the homogeneous transformation matrix. Why this is important? Homogeneous transformation matrix represents all the transformation as a matrix multiplication. Why we want to make everything as a form of matrix? Because we can transform n number of points which is there in space simultaneously by a single transformation matrix multiplication. This is an operator. This can be applied not just to a point or a frame in space or a vector in space. It can be applied to a set of points or those things. Okay, all the points, all the frames. It can be applied to vector, okay, position, anything, or solid body also. Okay, so just multiply this, everything will be transformed, everything will be shifted from one location to other, and it can be oriented. So how this is done, we'll see that later. So it represents all transformation as a matrix multiplication. Okay, it can capture composite transformation conveniently. That means it can do multiple things together. Okay, it can do translation and rotation together. Okay, there are many other transformation, but that is not a concern. In case of robotics, we normally are happy with just rotation and translation. Okay, but in case of computer graphics, animation and gaming, yes, there are scaling transformation also, when you can zoom an object, zoom in and zoom out. Okay, you can scale it, you can stretch it, you can shear it, right? There are many other transformations. Okay, but in case of robotics and robotics related animations also, we should be happy with having just rotation and translation. Okay, or any solid body transformation, that should be enough. Okay, so it can capture composite transformations conveniently, you see that. And change of reference frame, it can change the reference frame. You can represent something with respect to a reference frame, you can change that reference. If you know the relative transformation between two frames, you can express the same point in this new frame also. Okay, this point when expressed in one of the frame has a coordinate xy. Okay, if it is represented in a frame which is having a different position and orientation, will have a different coordinates, is it not? So if you know the relative transformation between these two frames A and B, you can now change the reference frame also. Same point can be expressed in new frame conveniently using this transformation. Again, different operations that are required to do this, we'll come to that also. Displace a vector or a frame. If you want to shift this vector to a new location, that also you can do. You can transform the point in this frame to a new location as well. Okay, you can transform this frame to a new location in a new way, or you can transform, keep the point wherever it is and just transform the frame to a new location. Okay, you can displace a vector also. If it is a vector which is connecting two different points, okay, this vector can be simultaneously, both the endpoints along with its magnitude and direction can be transformed together. Okay, it can transform a vector also. We'll see all those things. Represent a rigid body configuration. You have seen that a frame can be attached to a rigid body. If you can express a frame, you can express this rigid body as well. Okay, this frame orientation and position will give you the position and orientation of the rigid body also. So it can express the configuration of that. It is much easier to calculate inverse of a square matrix as well. We'll see why this is very, very important. Okay, that is a reverse representation. Okay, if you have a frame, you have a point. Okay, this point is with respect to this frame. Let us say it has x and y coordinate. If I express this frame with respect to this point, it will have a different coordinate. Okay, this frame can also be expressed with respect to this point. Okay, so this is an inverse operation, and that is done by taking inverse of a square matrix which is used to represent this frame. Okay, why, how, those things we'll cover later. So these are the importance of having represented a point or a frame in space using this homogeneous transformation matrix. Okay, you saw homogeneous transformation matrix. It looks like a 4 cross 4 matrix which has a sub elements which represents orientation and a column vector at the end which represents the translation. So it can simultaneously do all of them together. Okay. Going to next. Now translation of a translation matrix operator. Okay. As I told you, if the diagonal elements are 1, okay, you see it is here, diagonal elements are all 1. So it is not doing any rotation, because you see this is unit matrix, it is when multiplied with anything, there will be no change to that. Okay, so this doesn't do any change. That means this rotation thing, something which is responsible to do rotation, is not doing its job. It is simply doing nothing. Okay, so now you are left with last 3 elements. Okay, now see how this is working. Let us say you have a point P represented in space as Px, Py, Pz. So it is this point. Okay. Now I have a translation matrix. Be very attentive. These things are very important later on. So now this is a translation matrix expressed as 4 cross 4, because your point is now represented as 4 column matrix of 4 elements. So it has to be 4 cross 4 so that you can multiply them. Okay. So now you see, as soon as you multiply, what do you get? You see 1 into this. So it is Px, 0 into Py, 0 into Pz, dx into 1. So what it gives? It gives you Px plus dx. It gives you Px plus dx. Similarly, y is changed by distance, which is displacement, that is dy. Okay, Pz is changed by dz. You see, all the 3 point locations which are defined by Px, Py and Pz is now displaced by dx, dy and dz. So your new location is obtained, which is P dash. What is this? It is nothing but you have just added the components of d, that is dx, dy and dz to Px, Py and Pz, is it not? So you have reached to a new point location that is given by this. And what is this? This is nothing but P dash. Okay, so you have applied this translation to P, and what you have obtained? You have obtained a new point location, which is nothing but, if this is P, this is P plus D vector. Got it? So what this is doing? This is known as a translation operator. This is known as a translation operator given as a matrix of 4 cross 4. Now you know why this 1 is so important. This 1 could do this. Without this, you cannot do this. So why this 1 is important? In order to absorb this 1 over here, this last row has to be conveniently placed. Although this represents rotation, this represents translation, but this has to be there in order to make it okay with this. Okay, so that you can take the multiplication over here. Got it? So that is why it is very important. So that is why translation matrix will also have 4 cross 4 elements. Okay, and this is what is a homogeneous transformation matrix, which is not doing any rotation. Now let us see what next. Pure rotation. What we want to do now, we want to rotate, just rotate. We don't want to do any translation now. Okay, how to do it? Pure rotation. Let us say I want to rotate about this frame by an angle theta. So a local frame which is attached to the body, which is given by NOA, as you have seen earlier, that is attached to the body. If it is rotating about an axis which is passing through origin O, okay, that is this axis. Okay, so what will happen? O shifts by an angle theta, A also shifts by an angle theta, and it is rotating. Okay, this is how everything will change. Now I want to know the new point location after rotation. So what I am curious now, you have a point, you have a matrix which is when multiplied with this gives you a point location P dash. What is P dash? P dash is nothing but it is a rotated point about an axis x by an angle theta. Okay, so this is what I mean by pure rotation. Okay, and this is given by a R matrix. Symbolically maybe anything, but over here let us call it R to understand it. Okay, so R into P will give you P dash. What is P dash? P dash is nothing but rotation. So R is a pure rotation matrix. It is not doing any translation. Okay, so what we want to find out, okay, basic rotation matrix R, it is a 3 cross 3, which is a sub matrix sitting over here. Okay, you saw that earlier also. It sits in the heart of your homogeneous transformation matrix. This one, got it? So this is your 3 cross 3 matrix. Okay, that is what is doing rotation. So let us see how it looks like. Okay, so you have a frame OXYZ, that is the reference frame in open space. Your object was represented in this frame only. Okay, a frame which is placed on the object coordinate system was OUVW. It's a local frame attached to the body. Okay, so P is the position vector of that point. Okay, P is the position vector of a point which is placed on that object. Okay, any point which is there in that object only. Okay, so PUVW is the point which is expressed in the frame, object frame. Okay, initially it is aligned with the main coordinate axes, that is XYZ. PXYZ is the point expressed in XYZ coordinate system. Okay, so what I want to do, I want to apply P with a rotation matrix so that it gets turned with respect to this frame. So now new location of PUVW in XYZ frame is given by this. Okay, so PUVW is applied by a rotation matrix, and what I want to find out is PXYZ. PXYZ is the rotated point or the object point, the point which is located on the object, okay, in this frame. Okay, let us see how this is done. Okay, extracting the rotation matrix. I want to extract this rotation matrix. I assume this is done. I want to find out this, how this is done. So PUVW can be given as this, PUPVPW. These are the coordinates, these are the points with respect to UVW frame. IU, IV, JV and KW are unit vectors that is expressed in the object frame. Okay, so this is your point expressed in object frame. Now by scalar definition, if I want to see the components, if I want to see the component of a vector in a particular direction, let us say just start with just one vector, maybe a 2D vector. Okay, this is a vector V. If I have to take this projection of this along X, what I will do, let us say it is I vector. Okay, I vector, or you go to be more specific, I write it as Ix. So what I can do, I can simply write V dot Ix. Okay, and what does this give? It gives me component of V along X direction. Clear? Component of V along X direction. How? Because this is unit vector, it can be V into I, that is 1 cos of theta. So theta is the angle between these two. Okay, 1 is 1, so V cos theta. What is this? This is nothing but Vx. Got it? So this is what is represented by taking a dot product. So same thing, now I want to apply this in 3-dimensional space. So what I have done, I have simply taken dot product of this P to get the component along x direction. This is what I wanted to find out. Px after rotation, what is my new Px, new Py and new Pz. This is what I am interested in. Initially it was Pu, Pv, Pw. After rotation it has shifted somewhere. What I'll do, I'll simply take components of new points by taking dot products. So I have done what? Taken dot product with Ix. So Px is Ix into, okay, dot P. So taking dot product, either way it is same. This dot this or this dot this, it is commutative. It is same. So what I have done, I have simply taken dot product, substituted this here. What I have got is this first equation. It is quite clear. So Px is a component of this vector, a rotated vector in global frame, that is x, y, z frame, x, y and this frame, global frame. You have a point which is now rotated. This is a new point. I have taken projection of this to each of the major coordinate axes. Okay, that is the reference frame. Okay, so this is the first one. Second equation is the second one. I have taken dot product with jy. Specifically it is just j, or as it is in xyz frame, I have named it as y. Okay, otherwise I would name it as jv. Okay, jv. That I have not done because to distinguish between a local frame and the main reference frame. Okay, so just taking dot product, I got py. Similarly, I have obtained pz. Okay, without wasting much time here, effectively what I have done, I have taken projection of PUVW to the base frame, that is the reference frame, by Px, Py and Pz. So this can be expressed in matrix form like this, is it not? Just see what is being done just by taking Ix dot, what is being done. So you see Px is equal to Ix into Iu, Ix into Iu, Ix into Iu into Pu. Pu is here. Second term is Ixjv, Ixjv into Pv. Then similarly Ixkw, Pw, Ixkw, Pw. So this multiplied by this multiplied by this multiplied by this, is it not? So that is what is matrix multiplication is all about. You all know that already. So this is why this can be referred like this. Okay, now what this means actually, you have a point PUVW which is when multiplied with this gives you this. Is it not the same what we wanted to derive, that is rotation matrix? If you multiply a point which is in local frame points are not going to change. Let us say you have a cube, okay, you have a point on that cube. Okay, so this point PUVW, U, V and W, let us say you have a W frame also. So this point PUVW is not going to change with respect to its own frame. I want this object to transform with respect to this global frame. This is what x, y and z. Okay, so now multiplied with this rotation matrix, it goes to a new location. The coordinates of that point or that frame is now given by this. Got it? So it is pure rotation, there is no translation. I am just rotating this by something which is given by this. More specifically you will understand when we'll apply this. So don't stick at this location. We'll move ahead. We'll find out the physical significance by doing some examples now. Okay, so what effectively we did, we started with a point which was in UVW frame. I wanted to find out R3 cross 3 matrix which is when multiplied with PUBW gives me a new location of this point with respect to XYZ. Okay, so what I did, I took the components, expressed it in the matrix form and analyzed that, and I obtained what? R3 cross 3. Let us see how this is derived. Okay, let us see how it works when we rotate in terms of x. Okay, that means now the object is rotated by an angle with respect to x axis only. Okay, so what will happen? See, u, vector u and vector I, the angle between these two is 0 degree. So dot product will give you 1. Again IU and JV. Okay, I and J. I is along this, J is along this. So angle is 90 degree. So dot product will be 0. Similarly this, similarly this, similarly this. So what you get? Zeros in these locations. Why? Because you have 90 degrees at these ends. Okay, at these locations. Okay, so that is why it is 0. Now what happens to this? Why this is 5? Okay, so we'll see how. Look this closely. I'll wipe it off a bit now so that you can look at. Okay, so what is angle between JY and JV? JY and JV, both are J. Okay, this is in local coordinate frame, this is in global coordinate frame, reference frame. Okay, JY and JV angle is this. So it is directly, because it is counterclockwise, is taken as positive as a convention. Okay, we will take it as positive, so it is cos phi. Both are unit vectors, so it is 1.1 cos phi. So it is left with cos phi. Now similarly at this location you will find it is sin phi with a negative sign, because angle is in clockwise direction. This is phi sin phi. So it is quite simple. So this is what represents rotation matrix, a rotation matrix for rotation about x by an angle phi. Got it? So this is what. So this is your rotation matrix. What it does, this is when applied to a frame, it can rotate that frame by an angle. Okay, we'll again move ahead, we'll see more specifically how it works through some numerical example. Let us see how it does with a standard y axis and z axis. You try to do the same thing, try to substitute the way I did it with x. Okay, the way I did it with x, you try to do it for y and z axis as well. Okay, you do a similar thing. Okay, this time you draw a figure like this. You have 3. This time you are going to rotate about y axis by an angle. So there will be a shift like this. So this will be your new angles. Okay. Okay. So this is your y, and v will remain at the same location. Okay. This time there will be some angle between z and w, and there will be also angle between u and x. Okay, so this time this is rotation about y axis, and you can try that out at home, and this is how it is. Okay, when you do that you will get this. If you want to do rotation about z axis, you will get this. Need not to mug up the derivation of this. This is for now and on. You try to recall this, remember this forever, so that we forget it forever. We want to do robotics, we don't want to repeat mathematics. Okay, we want to move ahead. Okay, so let us do some alternative way which will let you understand things more clearly. This is for rotation about z axis. Okay, initially you had a point P. In polar way you can represent it as Px is equal to, initially you had coordinates as Px was given by r cos phi, py is equal to r sin phi. Quite simple. This is py, this is px. I want to rotate this by an angle theta, and reach to a new location p dash. Got it? I want to reach to a new location p dash. So now let us just express this p dash in our original frame, x and y frame. Okay, so that can be done quite easily. Px dash, now this is px dash, this is py dash. So what will be? It will be r cos phi plus theta, is it not? This whole of this angle is phi plus theta. Okay, so that is there, and py dash is equal to r sin phi plus theta. This is this height, py dash. So these two are there. Okay, so this is where you have reached after this point rotates by an angle theta. You want to know this point with respect to this. What is the rotation matrix? Let us derive that. So this can be expressed when you expand this trigonometrical expansion. If you remember, it will give you this, next one will give you this. Okay, this is cos theta cos phi minus sin theta sin phi, multiplied with r, it will give you this. Quite clear? Now substitute this here, you will get this. Clear? So px dash is now expressed as px and py and rotation angle. Okay, now I'll simply write it like this. So what you see, px, py, pz, over here pz is 0, this is 0, you just have px and py. This is when multiplied with cos minus sin sin cos, cos minus sin cos, and no rotation along this. Okay, this is rotation about z axis, so this is always 1. So what you see, it gives you pz remains unchanged. If it rotates about z axis, this is your z axis, only x and y will change. So new coordinates are these, is it not? So you can see this directly appearing here, px and py. So these two is here. So that is what. So what effectively this matrix is doing? This matrix is simply applied to a point, gives you a new point which is rotated by an angle theta, Got it? So rotated point you can get directly by multiplication, is it not? So this is how we'll go. So sequence of finite rotations are very, very important. So now what you see, you have something called a matrix, a homogeneous transformation matrix. Okay, that is when multiplied with a point, it gives you a new point which is a rotation matrix. Okay, so now how will you remember this? This is quite trivial and quite easy. I'll tell you. So if it is rotation about z axis, if you call this as z, this as y, this as x, what something you can find out, you have to remember it actually. You cannot derive it every time you need it. Okay, so what you will see, if it is to be rotated about z, this z is 1, this is 0, this is 0, column and rows are 0 and diagonal element is 1, and this is cos minus sin sin cos. Clear? If it is to be rotated about y, so this is 1, column and rows are 0, cos sin sin cos, but this time in case of y, cos minus sin sin cos, it is cos sin minus sin cos. Okay, in case of y it gets changed. Okay, what was there in case of x? In case of x, this was 1, this is 0, this is 0, cos minus sine, sine cos. So it is very easy to remember. If you have to rotate about x axis, put this as 1, these as 0, and cos minus sine, sine cos, and this is the angle by which you want to rotate. Done. So it is very easy. Okay, so this is how you can remember it. We'll use it very often, every now and then. Okay, so that is why. So composite rotation matrix is nothing but if the order of rotation happens one after the other. You have rotated by an angle about x axis, you have rotated about y axis, you have rotated about z axis, and you have reached somewhere, you want to know where it is. So you have to do things in order, and in reverse order if it is happening with respect to the global frame. So there is a point, okay, definitely it has to be in 4 cross 4 way. So all these will be 4 cross 4 if it is applied to be, if it is to be applied to a point. Okay, so this is the first operator. This is rotation about x by an angle alpha. This is rotation about z by an angle theta. This is rotation about y by an angle phi. Got it? So in reverse order you have to go. So this was the original point, multiplied with this you got a new set of point. Okay, new point. After this operator you got a new point. Now this operator will work on the new point, get another new point. Now this operator will operate. So this is how it operates. And finally what you get is a composite rotation matrix after all the rotation. So rotation has to be in order of x, z and y. It can be other order, it doesn't matter. Okay, accordingly you have to multiply. Just remember, you have to pre-multiply the matrices as and when it is applied. Okay, a point applied by rotation matrix, another rotation matrix, another rotation matrix, keep on doing like this. Okay, finally I got what? I got a composite rotation matrix. So you reach somewhere. So now you see, because rotation matrices or any matrix multiplication is not commutative in nature. Okay, it is not always commutative until unless it is a diagonal matrix. Okay, so over here you will find this, that applies to a physical thing also. That mathematics now can be seen physically also. Okay, so what I would assign you as an homework, because you have to do plenty of symbolic calculation, what I would suggest, these symbolic calculation, just to multiply these matrix, it's a huge task. Okay, because you have to multiply one after the other, many multiplications. Okay, many multiplications you have to do, and all symbolically, so that you get a general result, and it is very tough. So what I would suggest, use any symbolic computational tool, like in case of MATLAB we have it licensed. Over here you can use MuPad in MATLAB. If you haven't heard it, you start running this now. MuPad, through student login you can get into MATLAB workspace and do MATLAB without actually installing it into your PC. Okay, that is one way of doing it using MATLAB. There is a symbolic computation tool known as MuPad, or there is sims. You can define symbolic symbols using sims. Standard MATLAB code also can do this. Okay, Mathematica is a software also that can be used with Windows. In case of Raspberry Pi or Android also it comes. Okay, you can, it comes free with Raspberry Pi earlier version, I don't know now. Okay, so Mathematica also allows you doing symbolic computations. WX Maxima is a wonderful tool. It is supported in all the platforms nowadays. Okay, and this also can do symbolic computations. I would suggest you go for this. This is an open source, free and very widely used. Many online courses are using it, even MIT open course, I think. Okay, so these open source tools will be very helpful in doing robotics computation, because quite often you will require doing symbolic computations. Okay, These are the tools. Try it out and let me know if you have any difficulty. Okay, so this is what changing the order. If you do rotation about x axis, y axis and z axis, you reach somewhere. If you transform you in a different way, that means instead of going x, y and z, this time I went by z, y and x, you reach to a different place, because both of these will have a different result. It will let your point go to a different place. Mathematically, metric multiplications are not commutative. A into B is not equal to B into A. Okay, so that is why both the results are different, so the points are also different. So let us say you start with a book which is in this orientation, rotated by 90 degree about axis x. Okay, so you have rotated like this, you reached like this, rotated about x, then about y by an angle 90 degree. You reached this orientation finally. Okay, now you do other ways. You do first y by 90 degree. Okay, so simply it rotates like this. Next time you rotate by about x axis by 90 degree, you ended up in a different manner. Okay, so this is what it means physically. Okay, so you reach to a different place if you do change the order of operations. Okay, so this is all about rotation operation. Okay, we will discuss more later on in next classes. Okay, and that is properties of rotation matrix and few more things, why they are important, we'll talk about that. Okay, that's all I think for now. We'll end our class here.